Okay, welcome to module 2 of the Safe System Audit course. We had a great session last time, lots of interaction, lots of good questions. We could have delved into lots of the discussion a lot further, but we did cover a lot, which was good. This session, I'm quite excited. We start to really hone in on I suppose, the methodology of some of these assessments within a safe system audit. So the safe system assessment methodology, the auditing, how we write that up and the like. And we will, I suppose, expand on some of the principles that we discussed in the last session. Okay, so we're recording. We've hit the record button on this. And as we mentioned last time, your cameras are not able to turn on and we can't hear you. There is the option that you put your hand up and we allow you to unmute yourself. But the chat is the way we really like to interact with you, or the Q&A if you want to ask me a specific question. Right, I want to start with a risk formula. I'll give a prize out just to keep the prizes going. What's the sort of formula for risk? Anybody know that? Risk equals maybe something times something, or something plus something, or... Okay, good. Oh, right. So Bharat has come in with likelihood times consequence. Prize there. That is the traditional formula for risk, or I suppose the standard formula for risk. So likelihood times consequence, or probability times severity, or probability times consequence, or probability times severity. It's the chance of something bad happening multiplied by the magnitude of that badness, the severity of that. Now, I am also going to give a prize out to who was it here? Connell, because Connell was sort of adding their exposure, which is a little indication that Connell's probably got a bit of an idea of the safe system assessment methodology, which has extracted out exposure from likelihood, from traditional likelihood. So if we go back to normal risk, we say, like, that's the international definition of risk, not just for road safety, but we're talking anything. That's like financial risk, environmental risk, you name it. It is, what's the risk of recession? Well, what's the chance we go into recession? How deep a recession do we go into? But in road transport, the likelihood really encapsulated both the number of people exposed to a risk, then the chance that risk happens to come to fruition in a crash, then the severity of that incident. So when developing the safe system assessment methodology, which is the first component of a safe system audit, it was distinctly extracted out: exposure, likelihood, and severity. And we sort of touched a little bit on that at the end of last session. I'm going to keep sort of expanding on this, but just to show you, I suppose, from an infrastructure perspective, well, what sort of things would influence exposure and likelihood and severity in terms of the infrastructure chosen? Here's just an example of essentially closing off a conflict point, which is a railway level crossing in this one. And it's a bit hard to see in this photo, but there's a sort of mound of dirt and road closed signs on the other way. There is now no exposure to that crash. Like, you could phrase it that there's no likelihood of crash because nobody's there, but that's sort of like, it's driven by the exposure, the number of people exposed to that crash. Another one, sorry, and I should have said, count your wallies again in case that one on the last slide snuck through. The other one is like to completely segregate a road user group onto their own path in terms of uh, bicycles or pedestrians or shared paths, and the exposure to the crashes has been removed. The crashes being the vehicle to bike crashes, for example. Yes, there's still the possibility that the bike itself crashes, runs off the path, or crashes into a pedestrian or the like. But when you sort of isolate it out to the particular crash types, we understand that exposure has been removed. The likelihood of crash is all the things that you can do to lessen the chance a crash will occur. And we've done a lot of these in a traditional sense for a long time. So we've got things like geometric design, presence of shoulders, line marking, lighting, surface conditions we provide. And, you know, in a bit more recent times, we've started doing things like wide center lines, as you can see in that picture there, which actually I think I took sitting in the passenger seat in the car with Marcus, who's on this in this webinar. So all of these things, delineation, anything like that, is trying to stop the crash happening in the first place, and it lessens the chance of the crash. But with all of these, generally we see the same severity of crash if it happens. So the wide center line, for example, yeah, we're lessening the chance of a head-on crash because people have a little bit more time to recover. But if a head-on crash occurs, it's the same speed, it's the same sort of angle configuration, basically, and we're going to get the same outcome. Even traffic signals themselves, like, they only reduce the likelihood of crash. Okay, there will be some crash circumstances where they've influenced the severity a little bit, but what we see is that people drive through red lights unintentionally, also intentionally, and they are going at speed. Sometimes they're even pushing to try to go through and catch that last little bit of orange. So we see the chance of crash come down because it's clear in terms of the control, right? You stop, you go now, and the like. So less chance of a crash, but still when they do occur, the severity is just as high, if not higher sometimes, than a passively controlled intersection. So that's like a give way or a stop controlled intersection. But severity is associated with us managing some key variables that we can control. And we've got their speed, angle, energy absorption characteristics. So things like slowing vehicles at the conflict point will influence the severity. It could be raised safety platforms, raised intersections, and the like. When the crashes occur, the speed will be down, the severity will thus be less. And barrier systems, another great example. Hitting a barrier system is a crash. And in fact, putting a barrier system in place a lot of the time will increase the likelihood of crash because there's a lot more stuff to hit now. So putting a central barrier system like this one in place, well, we've got a lot more. There's just more chance that a driver will hit something. That's a crash. But the severity of every incident is going to be lower. Pretty much every incident. So it's a severity influencing device. Now, this becomes really important in a safe system assessment, being the first part of a safe system audit, because we need to critically analyze existing road network and any designs that are put in front of you to audit to say what factors in this road environment are influencing the exposure to crashes, the likelihood of crashes, and the severity of crashes. And you distinctly review each of these for different crash types and quantify them. Now, you quantify them with your judgment, right? But nonetheless, we're trying to put numbers to the exposure to different crash types, the likelihood of different crash types, and the severity of different crash types. And we multiply those through. And so I'll sort of take you through that over the next few modules. We're going to give you a little assignment at the end of today's session. It's a very quick assignment. You don't need to cancel your weekend plans or anything like that. It'll be very quick. You can do it from your desktop. But what it is essentially doing is trying to ensure that you have your head around this concept of what things in the road environment could influence exposure, could influence likelihood, could influence severity. So let's start with intersection crashes now. And well, intersections overall, understand a little bit about risk characteristics at intersections. And risk characteristics, just as I've talked you through there, is going to be the result of the exposure to crashes, the likelihood of crash, and then the severity of crash. Now, intersections are this really interesting point on the road network. And any of you that have analyzed any of the outputs of risk tools that are used on the road network, and there are lots and lots of them available, and they keep appearing. Kiwi Wrap, IRR, ANRAM, you name it. But anyway, we're not going to go into the details of each of those. But essentially, you can sort of have chainage along a road, so distance along a road, and you can have risk. And you'll sort of see that any road sort of bubbles along with risk and then spikes. Bubbles along and spikes. Right? And of course, these spikes are the intersections. There is an underlying sort of inherent risk, but at the intersection, it spikes. Now, it spikes because of a few things. Some are very obvious, and I'm sure you're going, yeah, of course it spikes because there's conflict points. There's the ability to actually crash with another vehicle there because it's crossing, the road's crossing, and that's absolutely one of them. And we see car to car, car to truck, car to motorcycle crashes at intersections. We also have the points that pedestrians will have to be crossing something, and cyclists will have to be crossing something as well. So that adds that bit of risk in there. But the one that people often don't think as much about is the runoff road increased risk that happens around intersections. The reason for this is twofold. One is that there is turbulence at this location. And by turbulence, I mean, there's vehicles that will make mistakes, enter the intersection. Vehicles then avoid, they don't want to crash, do they? So they'll try to avoid this errant vehicle that's entered into the intersection incorrectly or whatever it is. And they leave the road. So the chance that they leave the road is higher because of all this stuff that's happening. The severity actually is often higher as well because we, in our design and of intersections, just happen to put a whole lot of fixed hazards around intersections. We put things like signal pedestals. We put power poles because we need to turn the power line down the side road. We put lighting columns. We put culverts because we've got to get the water under these roads somehow. So we've kind of identified we've got this area of higher likelihood of leaving the road, and we've added all these things that make it really hazardous at this location. Now, often people just ignore that. Like, okay, well, it's a signalized intersection. We have to put signal pedestals in there. I don't really know from around the world of any great examples of really well-designed frangible signal pedestals and the like. But I'm keen if anybody can point me at those. I know the US does some funky stuff with stringing the lights over over the intersection on wires, so you saying their poles can be put back pretty far, which is quite interesting. But yeah, we just sort of ignore it, and I certainly have done road safety audits and safe system audits and the like, where I'm pointing out these things, and it sort of blows the mind of the designer that I'm saying you're installing 12 point source rigid hazards very close to the road in a high-speed environment, high-ish speed environment. And they're like, but that's a standard signal layout. And I say, I know, it's killing and seriously injuring lots of people. Anyway, so yeah, that's just one for you all to have a ponder about. So when we get to severity, we're really able to analyze things using our little severity chart, which we've had a look at, to give you that general gauge for what's the outcome when these crashes happen. And you can see we've got sort of the ability to think about trees and poles and these, what I call point source hazards, or what the industry calls point source hazards. It's a single point as opposed to a, you know, like a wall or a building, which is that more longitudinal style hazard. And you can see, you know, fairly low speeds get pretty serious pretty quickly there, don't they, when you strike those point source hazards. Side impact, cars versus cars, and that's the 90-degree type crash that we're talking about. You know, you get a bit more speed before it starts getting to those very serious territories. But we are thinking about that. Of course, general indication only, and professional judgment is required. But you'll notice that I start to talk about speeds and angles in there. I'm talking about right angle crashes there. This is back to your sort of year 10 physics when we were doing vectors, if you cast your mind back. But really, to explain this simply, is that with vectors, or we'll do it, with two vehicles crashing, the vehicle, some of the energy is pushed out like that. If you crash, with more angle on it, more of the energy is pushed out, as opposed to being directed into the other vehicle, if that makes sense. You can sort of imagine that. That's a harsher crash, that right angle, than sort of a bit more sideswipey, and the whole two vehicles push out together. So we know that about that 90-degree is about 50 kilometers per hour as that threshold limit, where we know things go really bad after that speed. It's not saying that everything below 50 is absolutely safe, guaranteed, but we know that it starts to really get really bad after those speeds, with small increases in speed. You can see, though, as you get some more angle on this, you're able to bounce a little bit of that energy out. So those sort of crashes can happen at slightly higher speed. That's there, says from Chemex. Chemex is the kinetic energy management model. It's sort of a detailed way to analyze angles and speeds and weights of vehicle to come out with kinetic energy levels. That is far more precise than you ever need to do in a safe system audit, right? Chemex, you're generally thinking about angles and speeds and presence of heavier vehicles and those sort of things, and getting this general feel for this this outcome that you think will happen. So rear ends and head-ons, we sort of have lumped together at around this 70 kilometers an hour. There's, again, lots of research, lots of debate out there around this. The thing that's probably important to know around this and all of these is we're talking about delta V. Delta V being the change in speed. So the reason I want to explain that is if we've got a vehicle that's sort of coming on an on-ramp, and we've got another vehicle coming along here, this can be done at very, very high speeds, and the delta V will be low, because we are talking about the difference in speed between vehicle 1 and vehicle 2. So vehicle 1 could be entering at 200 kilometers an hour, and vehicle 2 could be ticking along at 220 kilometers an hour. A delta V there is 20, right? So the initial crash, the transfer of energy is very, very low. Okay, and I stress the initial crash because that's going to be absolute chaos after that, assuming that they lose control and the like. So we wouldn't be able to likely operate that too safely. But the initial transfer of energy is what we're talking about in terms of that delta V. And that probably covers off this when we see, well, you can't feasibly operate an intersection above 80 kilometers per hour. That is, unless you're accelerating other vehicles and having them in those configurations. Okay. So when we look at new intersections or existing intersections, we start to use these key variables to understand what we expect the severity of outcome are. One is angle, one is speed, and then one is the vulnerability of the users, I suppose. Now, you don't need to be as precise as this little diagram. You can generally say, I'm going to change color here, so I'm not using red. You can generally say, okay, vehicle coming out here, struck by bullet vehicle coming through here. Okay, it's about a 90 degree. It's about 90 degrees, so I'm going to go about 50 kilometers an hour is threshold speed. Okay, when that vehicle, if that vehicle gets out and they're starting to turn, there's a bit more angle on that. So we can take that one and probably say 60 kilometers an hour is threshold speed. That's a kind of level of thinking that you need to do. There's probably enough talking out of me for now. Actually, I have to introduce you to this exercise. What I'm going to get you to do is utilize some of that exposure, likelihood, severity thinking in a little exercise here. So we've got a road. It's a sort of major highway. It's 70 kilometers per hour. It carries 22,000 vehicles a day. It's about 10% heavy vehicles, 10% trucks and the like. We've got a side road here, which carries about 2,000 vehicles a day, maybe a little bit more. It's got 50 kilometer per hour default speed limit, urban speed limit. This is, old residential area. This is a shared user path. That's some sort of drainage structure, a big drainage culvert thing. Sort of water flows in there and out here in some, when it needs to. That's a bus stop. It's a bus route. It's a heavy vehicle route, BW route. What else can I tell you about it? These are service roads. They changed over time as to whether they were two-way service roads or one-way service roads. They're just basically providing access to the residential properties. They have openings further down and further up as well. Up the road, probably 400 meters or so, there's a set of traffic signals, 400, maybe a little bit further. Down the road, at least, maybe a kilometer or a kilometer and a half is another set of traffic signals. Maybe a kilometer down the road, there's another set of traffic signals. Yeah, that's a bit of background on this site we're going to have a look at. Let's have a look at it from the ground, and you can see there, this is looking at that site we were just looking at. So you can see, there you go, the two-way service roads there, but you've got, a side road vehicle, you've got a turn lane. That's the bus stop that I was talking about. Let's have a look from the other side, shall we? Okay, there's the drainage culvert. There's a shared user paths over there. There's our intersecting road back there. It's got a sort of shouldery bike lane thing going on. So your task is to remove fatal and serious injury crashes at this location. I want you to change things however you want to remove fatal and serious injury crashes at this location. You've got a $4 million budget. Yeah. I'm always up for a 10% variation if you really need, but we're trying to generally stick around that $4 million budget. Now, I know some of you are already thinking, okay, well, I know exposure. Maybe I just close this whole intersection. Well, we've done all of the consultation and everything like that, and that's just can't happen. In fact, vehicles need to be able to get in. If they're coming from this direction, they need to be able to get in. If they're coming out, they need to be able to go both directions as well. So we need full access to this intersection going forward. The next one there, number 3, is you're operating in your current political organizational framework. What we mean by that is you need to try to at least give us a strategy if you're coming up with something extreme. If you said, I'm going to reduce the speed limit on the major highway from 70 to 20 kilometers an hour, I'd say, okay, how are you going to get that through the politics and the organization in your area of New Zealand? So you've got to be a little bit more, I suppose, considerate of the operating framework that we currently sort of find ourselves in. Now, within that, I'll give a little bit of leniency on exactly what policy positions are at the moment and the like, but let's go with something we think is possible. So the way we're going to do this, though, is that you're going to have a think about it. I've given you some background information, and then you're going to write it into the chat, but I'm not going to let you just write your answers. Like if you say, okay, we've got Josh has gone with an overpass of the main road. Okay, that's not enough because I want you to tell me whether that would influence exposure or likelihood or severity. Also, I remind you, you've got a $4 million budget. And if you're not sure how much infrastructure costs, I will be your instant cost estimator tool. So like for that, if Josh is asking how much for an overpass, I will say $47 million to do a full grade separated interchange style thing going on here. It's well out of your budget. And Penny's asking, yes, I'll clarify that again. You cannot ban right turns out and make it left in, left out only. We have to have full access in that general vicinity somehow. They have to be able to get in and out. So we want you to write your idea, but then put in brackets an E, an L, or an S, or a combination of those. If you think, okay, I don't know, maybe you say, we'll improve the lighting, which would be a weird thing to say. We didn't look at that at night or know what it is. But if you said, we're going to improve the lighting, that will influence the likelihood of crashes. We know that people will be less likely to crash at night because they can see the intersection, they can see pedestrians crossing, and they can see all these other things. But it's really doing nothing to influence speed or angle or the vulnerability of any road user or the transfer of energy, is it? It's just lessening the chance of a crash. Okay. Oh, Loretta's popped that in as a lovely example. Well done. Okay, I'm going to give you a few minutes on that. If you need a cost estimation on something, let me know, but I want to see you writing it in and telling us what you think it will influence. I'll give you a good sort of 3 or 4 minutes to do that. Okay, I'm seeing some good answers coming in. I'll give you another 20 seconds just to finish writing that in. Wow, lots of great stuff. I'm definitely not going to have time to go through everybody's everybody's answers. I like some of the answers coming in. Okay, let me just talk through a few of these, and I will sort of jump through them as we see common ones. I won't sort of repeat those. I might give out some random prizes as well. Okay, so I like Courtney's comment there to sort out that massive culvert risk, which will be some form of severity. I assume you mean by either a barrier system or extending it or something like that. I'll give Courtney a prize for just getting in quick with that one. Okay. We've had quite a number of people here looking to signalize this intersection. And we've had a little bit of variation on whether they're saying that influences the likelihood or severity or sometimes exposure. Some people are thinking it may influence. I want to really clarify this. Signalizing this intersection in a standard signalized intersection form only reduces the likelihood of crash. All right? So the reason for that, yes, there might be scenarios where people are conjuring up in their mind that there will be less, somebody will slow down, but still, crash at the intersection. But there is still that very reasonable possibility that a vehicle runs through at the same speed, the same angle, it's the same vehicles, the same vulnerability. And so we're only addressing the likelihood of crash through signalization in its standard form. I had a couple of people pondering roundabouts though, so another intersection form, and saying, well, and this one, quite a few people have nicely done there in the sense of saying that will reduce the severity of crashes because it'll slow people down. People will slow down. So if they do crash, have an intersection crash, it's going to be at lower speed, thus lower severity. And that's very much right. I'll talk about that a little bit more in a minute, actually. So we've got lots of then common themes there. We've got some people wanting to adjust this 70-kilometer speed limit down and saying that will influence. Some are saying severity, some are saying likelihood. It actually will be a bit of both. You'll get a bit of reduction in severity and likelihood for those speed limit reductions. I'm just jumping through. We had some interesting ones about some sort of changes to giveaways to stops and those sort of things. If they do provide any benefit, it will be the likelihood of crash. I don't think you'll actually get any benefit with that sort of change, but if you were to, it would be the likelihood of crash, just making it clearer who's got priority, where to stop, and those sort of things. So both the signals or the roundabout, neither are influencing the exposure to crashes, because exposure is about the number of people being exposed to crashes. So that's the number of vehicles going through, the number of pedestrians crossing, the number of bikes going through. Neither of those intersection forms are going to substantially change that. Now, maybe if you've got a traffic model that shows you, you put a roundabout in there, you're going to get like tens of thousands of more vehicles using this as a run. Okay, maybe you then got enough evidence to show, a change in exposure. But really, we don't see that the infrastructure in that sense changes exposure unless your traffic model shows you something like that, or your pedestrian prediction models. Just flicking through here, some really great answers. Okay, so Dem's gone a seagull intersection, which is a very interesting little idea. I'll give them a prize for thinking of seagull intersections, but I'll caution against seagulls shortly. But for those who aren't sure what a seagull intersection is, it's sort of like a seagull there, which would mean that you've got a sort of dedicated right turn, and then this white car would go into essentially an acceleration lane. And the reason I sort of like the general concept of 1 point is because we talked about delta V's and angles, and that all improves down here, which would be a reduction in the severity of crash at that location, right? The challenge you've got is that the merge from right is a horrible, horrible merge. A a lot of seagulls are just too short for that merge point. We have drivers who really struggle to turn their head and be able to make that merge. We have articulated vehicles. So, if it's a truck with a cabin or a container, well, they can't look back over that. They're really relying on mirrors. And so it's a really challenging one. Also, you still have that very clear side right angle side impact crash possibility over this side. So you're actually increasing probably likelihood of crash here. You've still got that. Severity will be down in this instant. There is actually a tool that was produced in New Zealand and is available on Wakatahi website, which is the Seagull Intersection Assessment Tool. So Shane Turner produced that with some others, I think. Apologies if I missed somebody who produced that, but that's a cool little tool to sort of analyze an intersection for seagull, whether it's an appropriate one, what the risk would be with a seagull. Okay, what else have we got here? So as people wanted to configure the left turn lane, the service roads, that's fine. Dion can have a prize for knowing how much roundabouts cost. Yeah, roundabout would be, so to put a roundabout in this location and to sort of meet general Ostro's guide to road design part 4B style requirements, it would be close to 10 million, I reckon, because it would have to be big and you would have to move all the services. You'd have to acquire land. It would just be a huge undertaking. I mean, your roundabout itself would need to sort of be that. You need to come out here, and it'd be really massive, because you've got to get these large vehicles around it. It's a multi-lane roundabout. You've got to provide enough sort of lateral movement requirements so that they actually do slow down. It'd be quite a beast of a thing. But interestingly, there's a lot of people who started to say, maybe we could do some sort of raised intersection, some sort of physical treatment to slow people down at this point. And just going back up to the top to see who was sort of first to start doing that. I think Marcus was first. We'll give Marcus a prize on that. Looking at sort of raised safety platforms, and then MJ6. Again, keeping Loretta on her toes, work out who that is. MJ6 has also said raised safety platforms, and then a few others have got into that. Now, that's a really interesting one. I've been running this course or variations of this course for about 12 years now. Admittedly, the first sort of 7 years, nobody was interested in the course, and then now a lot more people are, which is great. But certainly for the first 7 years of it, and I've been sort of doing this exercise for quite a few of those years, nobody would say raised anything on a major arterial like this. I mean, that would be crazy. And in fact, when I started my career, if I was to suggest raising anything on a major arterial highway like this, I would have been kicked out of the office, or at least laughed at and told to sit in the corner and think about the stupid thing I just said. Arterial highways like this, in the past, it was never, ever raise anything. This is about moving traffic flow undisturbed. You've got freight on there. You've got all these things. But we are evolving in our thinking around this. The concept of slowing people down through horizontal deflection, and I've got the horizontal deflection sort of on the screen there with like a roundabout. Everybody's comfortable with that. Okay, the cost of it, is a different matter. But to make people slow down to navigate around something, acceptable. To go over something had been not accepted on these roads. It was okay down on these roads, but not on those roads. And now that's changing. And it's really good to see this is coming through, and quite a few people putting that idea out there. And this is about really trying to hit up that severity aspect. Let me just unpack that a little bit more. We talked about the likelihood of crash being influenced by signalizing. Now, in that scenario, signals, they kind of make sense for a number of reasons. There are signals further up, there are signals further down. The configuration of that intersection is quite well set up for signals. In fact, I dare say when they did the original duplication of that road, they were thinking at some point in the future, this might be signalized, so let's design it so it could be. It's unbalanced flow. So we have a lower volume side road with this big volume road. So that kind of helps you with signals. You can control when these happen and the like. But signals are only going to influence the likelihood of crashes in their native form. And it's important to understand that signals are not a safe treatment. They are safer than a passively controlled, like a give way sign or a stop sign style intersection. But there's this little quick heat map of death and serious injury. And I just randomly picked out a bit of Auckland. I think that's Auckland. No, is that Hamilton? No, it's Hamilton. Some of you probably know the area very well. But, you know, signalized intersections. I think signalized. You know, we see, as I say that, I'm going, hang on, is that around? No, it is signalized. These are definitely signalized. This is out of Melbourne, out of suburban Melbourne. I mean, we just see the bulk of death and serious injury of intersections, when you're analysing intersections for most areas, are large signalised intersections. Now, there's an exposure element to this because we have a lot of vehicles crossing each other's path, okay? So we've got the exposure to crashes. But the idea that this is somehow the safest thing we could do at an intersection is absolutely false. Professor Jeremy Woolley from the Centre for Automotive Safety Research at the University of Adelaide is doing a review into a national road safety strategy. Anyway, he came out with this statement. He said, traffic signals are the biggest failure of traffic engineers. And I had a chuckle about it because he's very much talking from a safety perspective and the like. But the reason he sort of mentioned that, and he said that, was that traffic signals are generally thought about as there's nothing more we can do. Yeah, oh, it's got to this point, we'll signalize it. And yeah, okay, there's some little extra peripheries in terms of mast arms and maybe red light cameras, speed cameras at the intersection, fully controlled turns. But then, you know, it's not our fault if there's death and serious injury. They're obviously not obeying the rules. And at some point, after you analyze these long enough, you say, well, this is just ridiculous. We are putting in a design that requires perfect human behavior, which does not happen. And it's very, very clear it does not happen. Thus, we need to start to actually say, we have to change our design thinking. We have to do something here. And we see it all the time. We're building new ones exactly the same, and just for some reason thinking that everybody's going to perform perfectly at this new one. It's ridiculous. So a roundabout, though, is a different beast, right? In terms of the severity of crash comes down. We actually generally also, I'm going to sort of give a half tick on likelihood here. There's less conflict points. It's a much simpler intersection to navigate often. But you do get some increased rear end and side swiping crashes depending on your configuration roundabout. But it is all slower. It is much slower through these intersections. Pedestrians and cyclists, I'm going to put a little sort of, I'll put them to the side for the moment. Next session, we're going to have a lot of discussion, pedestrians and cyclists at roundabouts, how you can best cater for that, what the challenges are, how we make that as safe, because there are definitely challenges for pedestrians and cyclists. But from a vehicle-to-vehicle perspective at intersections, roundabouts are our safest form without going to full grade separation and completely separating. Vehicles slow down, they look around, the angle of crash is better. It's just a really wonderful treatment. In fact, we know that for cars here, if we put in a set of traffic signals, so we've got a give way sign, controlled intersection, we go to signals, we get about a 40 to 45% reduction in death and serious injury. If you go to a roundabout, you've got 80 to 90% reduction in death and serious injury. It's pretty impressive for a roundabout. It's not to say that signals don't improve safety, and that's a really important thing to understand. They just reduce the chance of crashes happening, but we still have this residual of high speed, high severity crashes at signalized intersections. There's much less of that happening at roundabouts. We see some run off road crash incidents and a few other things. But you talked about them needing to be super big, and you saw, if I go back here, you see how big this is. Sort of 2-lane roundabout. It's massive, huge land take, heaps of money, move services, lots of asphalt, lots of concrete, lots of lighting challenges. All of this is huge, massive dollars. I mean, really great safety benefit, big dollars. Could we go littler? Could we go much, much, much smaller? Different road environment here. There's different country actually over in the UK, and you see sort of these mini roundabouts, these painted roundabouts, these very small things. Well, one of the reasons you get such advantage with these sorts of roundabouts, you don't get that sort of 90% reduction, but you get a pretty hefty reduction in death and serious injury. And it's not as much about the horizontal deflection going around something alike. It's the disruption of ultimate priority. So a vehicle coming in here, vehicle coming in here, vehicle coming in here, nobody thinks they have like ultimate priority. If this was just a control by give way sign, the T would think that, oh, yep, don't need to slow down. This is my priority. Even if it's signalized, yep, this is my priority. I'm going through, I've got a green light, I'm going through fast. But this one, everybody comes in not thinking that they've got priority, so slows down, look around. This is the UK's equivalent of a 4-way stop that they do in the US or Canada. There's a couple in New Zealand as well. So that disruption of ultimate priority is really quite interesting. And you know, large vehicles can just track straight over that, so you don't need to worry about swept paths of larger vehicles and those sort of things. But very different road environment there. But just back to like road safety engineering 101, like roundabouts have a very small number of conflict points for that vehicle-to-vehicle crash scenario. Each one of those dots is what we call a conflict point, you know, an ability to crash. Signalized intersections, there's just lots of movement, lots of ability, lots of conflict points. We have that angle of crash I mentioned. It's a better crash. You just crash better at a roundabout than that high angle, high severity crash. And the third one, which I use this yawning guy as the one to talk about it, it's that people drive in all states of consciousness. So they could be very tired, they could have worked a double shift, they could be slightly intoxicated, they could be thinking about the fight they've had with their partner, they could be distracted by the kids in the back seat, you know, all these things, right, that take away their attention from the driving task. Gee, we'd love them all to be just absolutely alert and compliant, 100% focused on the road environment all the time, but they are not, right? And a set of traffic signals does a certain job in alerting them back to the road environment, right? But a roundabout does a way, way, way better job of activating them in the driving task. So they come back to reality, right? If they're half asleep, they wake up for a little bit to navigate through this roundabout, look around, slow down, right? And they carry on. Now, that's huge wins in road safety. Sure, I'm still got concerns around going back to their dazed state, but at the point of significantly higher risk, they are much more alert. And signals, like they do that for most people most of the time, but there's just a much bigger proportion that don't come back to reality, don't come back and be aware of the existing environment, and they'll run straight through that red light. Now, some of you have probably done that, and you've sort of gone, oh my God, did I just run through a red light? I mean, certainly I have no doubt you've driven in this non-engaged with the driving task phase. I mean, like if you've ever gone, oh, I don't even remember the last 5 minutes of driving. Like I've done it, but I wasn't really there and present. So that's how people sort of drive. That's what you get when humans are involved in making or in controlling parts of the system. So we need to do what we can in the engineering and design of the road environment to activate them in the driving task at different scenarios and cater for them when they fail. It's a bit, controversial, and you can get angry and get annoyed and say people should all just be, driving, alert and compliant and the like, but it's the reality of what we face. So if we look at roundabouts in a little more detail, this is a slight tangent. I just think it's fun, and well, there is some relevance to it in safe system auditing, but I think it's interesting. So roundabouts are exceptional, but the more lanes you add to a roundabout, the less exceptional they get, because people take straight lines through it. You have side swiping opportunities. You have incorrect turn movement, turning across other lanes and the like. So you can see here a little demonstration of speed and in a radius of roundabouts, of a double lane roundabout, a single lane roundabout. Speed's always a pretty good proxy for risk, essentially. Anyway, but turbo roundabouts, they're 2-lane roundabouts that basically operate like a 1-lane roundabout in a safety sense. So here's a turbo roundabout. A turbo roundabout essentially has a raised concrete separator on the approach and through the circulating carriageway. I mean, this is essentially channelized turn movements within a roundabout. It's pretty cool, isn't it? I love this photo in terms of it's a good demonstration of a turbo roundabout, but I love this. Like, we've got a truck that's come out here, a car that's coming up here. Mistake has happened. That truck's entered the intersection, or is entering the intersection incorrectly. But you can tell just straight away that it's going to be fine. It's going to be fine because there's no way that white vehicle can have enough speed to do significant damage. This is a radial roundabout. You know it's out of Europe just because there's sort of straight angle in and then around. That's sort of radial roundabout. New Zealand and Australia are probably tangential this roundabout, and you'd sort of slide in. But there's just no way that vehicle could be going at high speeds. That's great. So we know the severity is going to be down. Also, look at that angle. Beautiful. If they did happen to crash, they're bouncing off. If this was signalized and this truck made the mistake, which they're obviously in mistake-making mode, and entered in, and this white vehicle is coming through at speed, we've got a high speed and a harsh angle crash. Anyway, so there's a turbo roundabout. We don't have too many turbo roundabouts in the Southern Hemisphere. There's a few that are popping up, but I just thought I'd show you it out of interest. But this one's cool, isn't it? Like, this is a massive turbo roundabout out of the Netherlands. I flipped the photo because they drive on the right, and that would really blow our minds if we tried to understand what was going on here. We're driving on the other side of the road. But the reason I show it is more about the cultural difference. And we had a Dutch engineer we brought out to do some work with us on cyclists at roundabouts, design of roundabouts to improve cyclist safety. And I just happened to show this to the guy and said, yeah, this boggles my mind. I mean, I love it, but just the sheer land take, the size of the thing, and the sort of complexity of it, it's amazing. And here in Australia and New Zealand, sort of after a bit of a chat, I said, like based on the volumes and what this area was, I said, yeah, that'd be a large signalized intersection probably. Maybe it would have got to a grade separated interchange, but probably a large signalized intersection. And the Dutch engineer's like, but what about all the death and serious injury to your community? And I'm like, yeah, I know. It's just, yeah, he could not fathom that we would possibly run a high-speed signalized intersection without some major traffic calming to get vehicles to appropriate speed. And they would rather go this sort of thing, which is signalized, by the way. And he explained, and I can sort of see it. It's not actually as complicated as it looks when you're on the ground, because you just sort of follow your path and you go through. But you've got to slow down to navigate through it. You're very clear you're approaching an intersection. It's going to wake you up. You're going to be involved in this driving task. So more from that, philosophy perspective of, it would be absolutely ridiculous for the Dutch to ever let one of the intersections that we build hundreds of every year just without even thinking about it. It just would never happen. But it's interesting to see lots of people are playing around with intersection design of our standard large signalized intersections to say, well, okay, we know we need to get traffic through, and we don't get as much traffic through a roundabout. We know it's got the safety benefits, but then we're adding lanes, and that's a challenge. And what characteristics could we put in that would enhance? And this one's the idea that you could at least do something that would be a physical presence in the middle of the intersection, wake people up, alert them, make them slow down to navigate horizontally around something, improve some angles of crashes, but still maintain pretty massive throughput in terms of traffic on your big sort of traffic sewer routes. This is a concept. This hasn't actually been built. But yeah, it's interesting that people are looking at it. Anyway, the principle I'm trying to put across is that, a large high-speed signalized intersection is, it doesn't align with safe system principles. Because when you go back to those fundamentals, people make mistakes, crashes will happen. We need to make sure they're not death and serious injury. That just does not line up. So road safety platforms, we talked about that, and really heartwarming to see so many people going for this. These are not urban speed humps. They're more shallow. They are designed with grades and ramp lengths to just dampen speed down to appropriate speeds. And this was the design for that intersection that you were looking at, which was they also came to the conclusion it needed to be signalized. It needed to be signalized because of the unbalanced flow, signal linking, costing. They wanted to provide some sort of pedestrian crossing. There are not a lot of pedestrians in the area, but they did want to provide something. So they said, yep, signalized. But then they said, well, our top 50 intersections for death and serious injury in our region are large signalized intersections. Are we really just going to build another one and say, maybe this one will work? No, we've got to do something else. We've got to start addressing the severity. And they opted for raised safety platforms on the approaches here. And they didn't do it for the side road or raise the whole intersection because they didn't need to. The vehicles coming in and out, that's not a bullet vehicle. The vehicle coming out here is not a bullet vehicle. They don't have enough speed to do damage. These are the bullet vehicles. That they are the ones that have the speed to do the damage. So you've got to get that bullet vehicle speed down to a range that you're more comfortable with. Now, their primary thing they were trying to address was the vehicles coming out, the vehicles going in, being struck by these bullet vehicles. So what speed do you think they were trying to get these vehicles down to? Remember, this is a major arterial, and you know, a lot of people going through there. What speed do you think they were trying to get that down to? Yeah, 50. All right. 50. Lots of 50s came in there. Loretta, I'll let you work out. Give prizes out to the first couple of people who said 50. Now, the reason 50 is because, remember, if we go back to our angles, speeds, what's the trigger before things start to go really bad really quickly? This is about a right angle crash, right? That's about right angle. So we know about 50 is our limit. Now, yeah, we could go try and get much lower, but they're trying to, you know, continue to maintain this as a major arterial highway. And they just dampen it down to 50 because they know it's higher than 50, it's going to be really bad. Lower than 50, we know it's not absolutely perfect, but it's going to be pretty good for that type of crash. If they were saying, no, we want it to be absolutely, as you know, pedestrians are the major concern here, they would try to get it down to 30. And by that, I mean, that's the length of the ramp, the angle of your ramp. You can change it and you will elicit speeds of bullet vehicles that you want. I've got a cool little tool that calculates that based on your ramp grades and lengths, exactly what speeds you'll expect to get out of the bulk of your vehicles. Of course, there are lots of different vehicles and suspension and all this sort of stuff. So it varies, but you know pretty much what you're going to get. Anyway, so yeah, there they built it. And you can see 50 advisory speeds. That's another interesting one. 70 kilometer per hour advisory speeds. People get less irate when you say, hey, we advise you go 50 because you're going to have to navigate over this and it's going to wreck your car if you don't, rather than if you put a regulatory 50 and a speed camera there. They get really irate. This is revenue raising. You're trying to catch people. They're not objecting to going a slower speed through the intersection. They're objecting to us. They're objecting to government intervention regulation, essentially. And so I was out there with a colleague doing the post-opening audit of this and took this photo. I love this photo in the sense that you've got a vehicle braking on the approach to a green light. Now, my friends in traffic operations, they get angry at this photo. They're like, oh, it's so inefficient. Why are we slowing everybody down to go, you know, when there's just 1 in a million chance that somebody's actually going to crash? Well, what are you talking about? If we built a roundabout there, everybody would slow down and you wouldn't be arguing about that. It's just because this is not something we've been doing for the last 50 years. So, yeah, anyway, that's another like little side spin-off benefit is a reduction in the dilemma zone. So for those who don't know what the dilemma zone is, that's a traffic engineering term. And again, prize for like whoever named this dilemma zone. It's the best naming of something, a concept ever, in my opinion. The dilemma zone is the point in time and space when a driver sees, when the signals turn orange and they're in a dilemma. Do I put the foot down and go, or do I brake? And you can calculate dilemma zones. It's cool. the dilemma zone basically shrinks to almost nothing with the addition of the raised platform, because the driver already has their foot on the brake. They're already slowing down, goes orange, and they just brake. There is a very small dilemma zone left, but it's pretty awesome. And these are starting to emerge now as a bit more common practice. I know you've got a challenging road safety government policy position in the pipeline, which is a little hesitant to this sort of approach, and that you'll work through that and we'll adapt. But nonetheless, here's one in Hamilton, which is working beautifully. It's wonderful. Again, same concept. They raise the sort of whole intersection, or you've got to goes up and then it slowly can come down. We're now addressing likelihood with the signalization. We're addressing severity with the raised platform. We're actually doing much more to align very highly with safe system principles. One out of Christchurch, which is raising the full intersection. Again, of course, you get community grumbles about these sorts of things because they're new and they're different, and it's changing the way people use an intersection. But it's going to prove as far less death and serious injury. All right, maybe I'll give people a quick stretch break. I mean, we sort of had a break. I'm just going through lots of raised signalized intersections. This one's got 54,000 vehicles a day on one leg and like 28,000 on the other. These are big intersections. And I'll leave it at that point with the Austroads guide or Austroads information about race safety platforms, written by New Zealanders too, this one. So that's pretty cool. Let's take 3 minutes. That's enough time to have a stretch, fill up your coffee, and we'll get back into it. Okay, I better get back into it. I've probably got another 2 hours worth of content to get through today and not that much time. That's okay. We'll get you to the point where you'll be able to do your little assignment, which I think really consolidates the thinking and helps you get your head around that exposure, likelihood, and severity. You're mostly doing really well with that little exercise we did before. Anyway, there's the Austroads document. Austroads documents are free. Just get your login for the Austroads website, download it free. There's some Auckland Transport design notes and the like about raised platforms as well. So good information available. I popped this up there just out of interest. We talked about, big roundabouts, and then, we have been playing around with compact roundabouts quite a bit and trying to understand, can we create roundabouts that give us the same sort of outcome at a much lower cost? This is a compact roundabout we were involved in. Very small circulate radius roundabout, reasonably big concrete apron, and essentially, large vehicles really track around sort of like that in order to get around. Lots of concerns around it's a bit straight. It's a bit straight through this whole thing. So use of some raised platforms to slow vehicles on the approaches as well. So it's actually a couple of them. You see one there. You usually use reverse curves on the approach. So you sort of chicane people into a roundabout to start slowing them down. This one, without trying to buy up too much land and the like, trying to do that with some shallow raised platforms and then a slightly harsher raised and then into the roundabout itself. So it's a pretty good example. It's about half the cost of what a full-size roundabout. So it's not like it costs nothing, but it's pretty great to be able to sort of halve your costs, maybe get double as many intersections treated associated with this. And we pretty much, you can't really get comprehensive evaluation from a crash perspective from one side. It's just statistically ridiculous to try to do that. But in terms of monitoring speeds in and general compliance and these sort of things, it really is performing just as well as a full-size roundabout. Happy to send people the detailed designs of that if they've got a particular interest in particular aspect, be it, there's all sorts of challenges and fun in designing those. And we wrote a road design note guidance for the Victorian government on how to think through some of those particular aspects. That's available publicly as well. Loretta, I don't know if we've got a quiz or I need to just keep ticking on.
We do. We'll just launch that now.
Oh, it's a one-question quiz. Oh, I like it. True or false? Traffic signals are not safe system. True, false, or unintelligible question? Unintelligible question meaning your question doesn't make sense, Ken. I'll let that go in. Now, I should be asking Loretta, as we got this little pause here, about any questions that might have come in the chat or the Q&A.
No, nothing. I mean, some great discussion and interaction with the group, which has been, really good. Thanks, everyone.
Awesome. And it looks like we've got a compact roundabout on State Highway 2. I'm intrigued. I'll have to go have a look. All right, let's end that now. Okay, it's a little bit of a tricky question, and you certainly don't get marked for it, but we've got a fairly even split across true, false, or unintelligible question. The reason I popped this question in is, first of all, I have had people leave this course and go, "Oh, traffic signals are not safe system. We can't ever do a traffic signal again." And I'm like, no, misinterpreted what I was trying to say there. The signals themselves are not like that. It's irrelevant. It's the context of putting signalization in. So if you said true, I assume you had a particular context in mind, like a high-speed signalized intersection. I can understand that. If you said false, I assume you were saying, well, it's not the signals, like it's where they're placed and how they're placed and what environment it is. If you said unintelligible question, that's probably a pretty good answer too, because of this. There's no context to that question. It just doesn't really make sense. Also, another one is that we don't tend to talk about the safe system as a binary concept. Don't say, oh, that's not safe system or that's safe system. It's what is the alignment with these principles? Because we know it's a spectrum, something that is absolutely purely fully safe system. A closed road is probably it, possibly. Even that you'd really but it's just got super high alignment with safe system principles. But yeah, so I try and talk about it as a spectrum. And you'll see when we do a safe system audit, we're doing that first part of it, the safe system assessment part of it. We give a score out of 448, and your project will, or the project you're looking at, will fall somewhere on that spectrum. Okay, let's get rid of that. Oh, did it? Sorry, did I? I'm not even sure we shared those results. Anyway, it doesn't.
Yeah, we did. We did.
We did?
Ended. Yeah.
Okay, thank you. Sorry. Okay, let's briefly talk about lane departure crashes. Now, lane departure is either run off road and hit poles and trees, or roll over or hit culverts or these sorts of things, or depart the lane and have a head-on crash. We generally categorize those as lane departure. Leaving the road and striking poles, trees, is an incredibly violent incident in terms of energy transfer. Okay, that point source hazard directs the energy into the vehicle at just stunning proportions. And so that's why in our severity charts and things, you see run off road into poles and trees, we can really only survive those at a side impact crash like the one you see on screen if the strike is around that 30, 40, maybe if you're lucky, 50 kilometers an hour impact speed. But we see this happening way faster than that. And it's really, really severe. But so much of the New Zealand road network is just trees and poles and culverts, and then often just separated by a white line. And if we crash head on, we know it's around that 50 kilometers an hour, 70 kilometers an hour or so, where it's generally survivable up to that. But above that, we're in pretty bad territory. So, here's a sort of classic bit of state highway, and you just see like these vehicles, they have to stay in their lane to survive. Okay, if they're lucky, they get a little bit of they leave their lane either side, they get a little bit of recovery area on the left. On the right, they may get a bit of a recovery area if there's not a vehicle coming the other way, but if there's a vehicle coming the other way, there's not much recovery area. So we're really just sort of running this tightrope of death and serious injury either side. So it's really in a road environment that does not align well with safe system principles, because mistakes result in death and serious injury. And I talked about the inherent weakness. Now, weakness is not necessarily a bad thing. Inherent non-energy absorbing characteristics of the side of a vehicle. This is the side impact pole tested, the old one, 29 kilometers an hour. It's crushing that vehicle pretty badly. You can imagine vehicle occupant sitting pretty close to that. The ability of the side of the vehicle to protect us is a challenge. Here's one that this is quite a violent crash coming up. 60 kilometers an hour is predicted at 60 kilometers an hour based on the frames of it. So you can see just the huge violence in that in terms of energy transfer. It's not expected to be survivable. So clearing the road of all those hazards is a logical thing to start to think about. Okay, so can we get rid of the poles? Can we get rid of the trees? And that certainly in the first sort of 4 meters does a good job at reducing the number of death and serious injury. So run-off road casualty crashes per 100 million VKT. VKT being vehicle kilometers traveled. That's your sort of way you would compare like for like. You get that sort of big benefit, but it's pretty interesting as it kind of flattens out. So we're not eliminating risk, we've reduced it, but it flattens out. Asymptotes out at around 4 in this work that Ostrodes did. So these are people rolling over, going beyond whatever distance has been cleared, finding trees, finding poles. So there's still that risk out there. So the old concept of clear zones, it's not necessarily a safe place to be. It's not a highest alignment with safe system principles. It's pretty valid if you're able to achieve it for first 4 to 5 meters, but this was essentially the best way we could think about managing a roadside 10 years ago, maybe 15 years ago. That's because barrier systems weren't that advanced. There were things, certainly, that you could put in there, but we were always worried about them as a hazard and people spearing and vaulting and hitting them badly and all these sorts of things. But barrier technology has just gone off the charts. Like, it's so advanced now that putting a barrier system around 4 meters, 3 to 5 meters essentially off the edge line, it's actually safer than clearing 10 to 15 meters of cleared roadside, because there's less rollover risk and vehicles can't get beyond that. So really, when we think about high alignment with safe system principles on a length of road, sure, we've got our big roads and the continuous barrier systems, like you see here, are the highest alignment with safe system principles. When a vehicle leaves their lane, leaves the road, they strike a barrier system, they run along it, they dissipate their energy. The design of this road is that people will make mistakes and we will protect them from death and serious injury. And it's fairly consistent with what the new Austra's Guide to Road Safety Part 6, Austra's Guide to Road Design Part 6. Got to be careful with that. There's a Austra's Guide to Road Safety Part 6, and there's an Austra's Guide to Road Design Part 6. Give a prize if you can tell me what the Austra's Guide to Road Safety Part 6 is about. This one's the Austra's Guide to Road Design Part 6, which is roadside design, safety, and barriers. Nobody's going to have a guess at that. The idea of the safe system, fully contained roads is very much sort of integrated into this. And Courtney is on it. Road Safety Audit. Yes, Road Safety Audit is the Austra's Guide to Road Safety Part 6. The highest alignment with safe system principles are continuous barrier systems. Continuous flexible barrier systems, some people call it the bumper bowling of roads, but you essentially assume your vehicles are going to leave the road and you contain them. The little analogy people like to give often, and I was at the Safe System Engineering workshop and I gave this analogy, and then Fabian gave this analogy, and then somebody else gave this analogy. It was sort of popped up a lot. If you were building a high-rise building and you had balconies, you would put balcony rails, right? No ifs, buts, or ands. You would put railings. The way we have operated our road system in the past is to put a white line. And then, if we were worried about the risk, extend the balcony a bit. And then put some warning signs up. The energy of the fall, 100 kilometers an hour, it's like the 5th or 6th floor of a high-rise building. You're going to die if you hit a tree or a pole or a culvert or the like. So why are we thinking about the roadsides any different to these? We put absolutely stock standard that you would put a barrier system. You don't need to go all the way back there. Okay, so the Safe System Audit Guidelines are there. They're available. I could tell you website. They're still taking feedback on these. The Safe System Assessment Framework is the first component of this. So that's what we're going to be starting to do, is really do some safe system assessments of designs and existing roads and the like, and get that practice. And then we do a bit of road safety auditing. So a safe system assessment, the first part of this safe system audit, one of the outputs we want is something that looks like this. And you can see here that we've got runoff road, head-on, intersection. These are crash types, aren't they? And these are passenger vehicle crash types. We've got other, which I'll talk to in a second. And we've got crashes involving pedestrians, cyclists, and motorcyclists. These are the crash types that kill and seriously injure New Zealanders. The other sort of caters for anything that's slightly been missed in any of those other ones, but those other ones are the bulk of death and serious injury of New Zealanders. So what we'll do is we'll look at an existing road and a road design, and we'll say, what is the risk of runoff road? What's the risk of head-on? What's the risk of intersection crash? What's the risk of a pedestrian being struck? What's the risk of a cyclist being struck? And what's the risk of a motorcyclist being struck? And we will try to quantify those. Now, this one just happens to be for an intersection where they are saying, Well, we could build a roundabout there, or we could do traffic signals with a modified T, or we could do traffic signals with a conventional T intersection. So they've obviously got a couple of ideas in mind. The red here is what exists at the moment. That's the risk with whatever's currently there. And then the orange, blue, and gray are different options and their alignment with safe system principles. So that's sort of the product. One of the first things you want to do in your safe system audit is produce something like this. The way we do that is to utilize a thing we call the safe system matrix or the safe system assessment matrix. It could be called table, the safe system assessment table, but what it has is exposure, likelihood, and severity as the rows. So that's why I've been banging on about exposure, likelihood, and severity. And then across the columns, we see these different crash types that I just talked about. Run-off road, head-on intersection. Now, these are vehicles, because then we cover off pedestrians, cyclists, and motorcyclists over here. Other will be any crash type you predict that doesn't neatly fit into those. And examples of other crash types in safe system assessments are railway level crossing crashes, side swipe crashes, crashes with animals, sometimes e-scooter crashes where you are saying, okay, it's a very distinct element in its own right here. I'm not comfortable having it as either, mixed in with pedestrian crashes or mixed in with cyclist crashes. I want its own entity. You use the other column in that circumstance. And I want you to think about these like crash codes, like crash. If you were doing a crash reduction study or the like, if a pedestrian is struck at an intersection, you account for that in the pedestrian category. Yes, it happened at an intersection, but we're thinking crash type, not spatial location. If a vehicle runs off the road and you're worried about the vehicle occupants being injured, that's run off road. If you're worried about that vehicle running off the road and going through a bus shelter where pedestrians will be waiting, that part of it is the pedestrian crash. Think about which occupant, which road user is going to be the one injured in the crash that you are predicting or foreseeing. That's a good way to sort of think about it. Then we go into, okay, what's the exposure to crashes? What's the likelihood of crashes? And what's the severity of crashes? And we will go through and we will, in our safe system assessment, we will write notes on these. We'll write lots of notes about things that we identify out there that make us, think that this could be an issue or is not too bad. We're writing lots of things down. There's some examples in there. We're going to go through this in detail next session, so I don't need to do it now. I wanted to introduce you to the concept for now. Next session, we'll dig into the details of this, and then we'll be getting you to practice sort of filling out some of this detail later. We end up multiplying. So after we've put details in here, we give scores, and then we multiply down. And that's how we end up with numbers. There are these scoring reference sheets. So we know what a score of 0 would be, a score of 1 would be, a score of 2, 3. So we use these to get a bit of an idea. We've written lots of information and we put a score in. So we might put a 2, or after we've analyzed and written things down, we might put another 2 here. We might put a 1 here maybe, and then you multiply those down. So you get a total score of 4 for run-off road, for example. Okay, I'll take you through that in more detail later. I just wanted to show you the concept of how you sort of arrive at scores based on crash types to get us to those graphs that we were talking about. Probably makes a little more sense now why we had some numbers here. It's going to help you with your severity scores. because you'll be able to refer to this, say, oh, that looks like it's about a 3, or oh, somewhere around the 2 or 3. Maybe I'll take a 2 for that. You'll be able to get a little bit of guidance from this. I'm actually just going to jump back and show you a little bit more detail on this before I get Loretta to introduce you to the assignment, just because I want to make sure we're pretty ready to get into this next session. So you'll see here under exposure, we have AADT, basically, pedestrian numbers, cyclist numbers. So, okay, if you had AADT of, say, 3,000 vehicles a day, the AADT being annual average daily traffic, how many vehicles are using this road? You can't put 3,000 in there because that's not between 0 and 4. You have to go to the scoring reference sheet and say, okay, exposure. What are we saying here? Well, that one's no exposure. That's what's a 1. Vehicle volumes might be involved in a particular crash type are low, therefore exposure is low. For run-off road, head-on, or other crash types, AADT is less than 1,000 vehicles a day. No, we've got more than 1,000. I said 3,000. Okay. AADT is between 1,000 and 5,000. Okay. There we go. And that score is a 2. So then you go back and you take that and you put a 2 there. So it's sort of as simple as that. Pedestrian numbers. Yeah, if you're given pedestrian counts in the area, great. You can use that because you can go again to here and say for cyclists, pedestrians and motorcycles between 50 and 100. Or between 10 and 50, or greater than 100. So you've got that reference sheet to go to. If you're not given the numbers, and often that is the case, they don't have numbers, you just make your prediction based on what you see out there, what you know of the area and the like. So you're sort of quantifying exposure. You do that across the board. Then likelihood, you start to list all of the factors you see at the intersection, in the design that influence the chance of a crash. And you can see some examples here: speed, geometry, shoulders, offset to hazard, delineation, guidance, could be surface conditions, could be, is the area subject to fog? Like all of these things, you'll be dot pointing ideas out. And then you will make a call based on this little bit of guidance that they give you in likelihood to say, it's highly unlikely that a crash will occur. It's unlikely, it's likely. Now, remember, we have already accounted for exposure. So you're not doing this. You're not saying, well, it's unlikely that a crash will occur because there's hardly any vehicles there. No, we've accounted for that. We've accounted for the fact that there's hardly any vehicles there. You need to think about that from an individual perspective, using an analysis of the infrastructure, the likelihood of a crash, and you can kind of do it in a relative comparison of other infrastructure and the inherent sort of chance of crash associated with physical infrastructure. So there is subjective judgment associated with that. I don't deny that. And it's no different to other risk assessments where you're making a call on some of this. And then you do the same for severity. And a severity, I mean, we've got speed, we've got the severity of hazards being struck, or we've got presence of heavy vehicles, larger vehicles carrying more mass, carrying more energy when things happen. It's going to be worse. Speed's huge factor in this. Impact angle at intersections, another one. So you sort of go over here. It's got some information in here. It talks about kinetic energy and what you're predicting in terms of the outcomes, and that you should use safe system, threshold speeds and the like. Well, this is essentially what this graph does to help you out. Okay, so that was an introduction to that. We're not going to get you to do a full working of a safe system matrix as your assignment. What we're going to do is make sure you really have your head around what influences exposure, what influences likelihood, and what influences severity. And the way we're going to do this is to get you to pick an intersection. This could be the intersection out in front of your house. It could be the one on your way to work. It could be one that you remember from a holiday. It doesn't matter. You're not actually going to need to go to this intersection if it's not convenient. You can do it from Street View, whatever it is. This one's less about the absolute precision of it, more about the concept of categorization into exposure, likelihood, and severity. And Loretta will show you shortly how you get this in the learning management system and upload it. But I'll explain it while I've got it here. You've got the first thing you'll see is an instruction sheet, okay? And it gives you the steps to follow. So you'll be able to just follow that. You put your name in. Anything highlighted in yellow, you're going to have to do something with. Put your name in. Then you put like a link to the street view or the coordinates of your intersection. So the people marking your assignment can have a dive in and have a look as well. But this is where you're going to put stuff. So exposure, you've got 3 columns here. Exposure, likelihood, and severity. And this is proving you understand this concept. It says, so for that intersection that you've picked, for the existing conditions that are currently there, what are factors that influence the exposure to crashes? So minimum of 1 factor, maximum of 3. So this could be, it's a major arterial, or this could be, this has got a major pedestrian desire line from the bus interchange to the shopping center and lots of pedestrians cross. Those are exposure. Then you do likelihood. And this is where you would say, okay, well, the intersection has got, it's got a see-through effect, or it's unclear exactly which leg goes where, or it's unsignalized, it's passively controlled, or it's got poor surface conditions, whatever you sort of see that influences the likelihood of crash, or it's, high speed. Then, so you're doing, again, between 1 and 3. And then you do severity, between 1 and 3 things that influence the severity of the crash when it happens. And really remember, like we've done severity a few times now, speed, angle, vulnerability of user, these sorts of things are the key thing. Amount of heavy vehicles could be one. So of what is currently there, you do between 1 and 3 for each of these. Then you go, right, tell us one thing you could change that would influence exposure. One thing you could change that would influence likelihood. One thing you could change that would influence severity. Just one thing. Just the way we did with our raised intersection, or that signalized intersection we were looking at. One thing you could change that would influence that particular aspect. Okay, I hope that makes sense. Loretta's now going to take you through the learning management system and show you, how do you find that sheet? How do you upload it? How do you make all of that happen?
Thank you. Ken, you can see my screen there?
Yes.
Excellent, thanks. All right, so this is, as you know, the learning management system. So we've completed module 1 onto module 2. So 2 tasks to do, the one that Ken obviously just explained, but firstly the quiz. So we'll give you a few minutes back to complete the quiz, just like module 1, clicking on the quiz and attempting that quiz. In regards to the assignment, so clicking on this assignment section, and those instructions are repeated here. Once you click on this document, that's the Word document, so that will appear. And as Ken mentioned, anything in yellow is what you need to complete. So filling out that Word document and then saving that. You can save it as a PDF or a Word document. Probably PDF is always better. And then you need to submit it. So firstly, clicking on the Add Submission button, and you can either do a drag and drop it in the box, or you can upload the file. So you add the file in there and save the changes. So this assignment is due by Monday. So that's pretty much how you submit your assignment. But yeah, just filling out those yellow sections and then submitting by Monday. Ken?
Oh, I think you've described it well. Opportunity now, if anybody has any questions, either about the assignment, the quiz, or the content. Otherwise, we're going to give you 9 minutes back to finish your quiz, and you get a good crack on that assignment as well, I believe. Don't write us like pages and pages of information in that assignment. We just want very brief dot points, and you only need to do between 1 and 3 and 1, and it can be a very reasonably quick assignment. You remember, it is primarily about, do you understand what exposure is, what likelihood is, and what severity is, and you just need to prove that. Awesome. Thank you.
Thank you, Ken, and thanks everyone for joining us again today.
Okay, I'll see you all next week. Have a good weekend.
See you then. Bye.
Bye.